In this lecture, I'm going to introduce a family of numerical methods that we can call all of them variational methods. Unfortunately, and unlike other lectures in this series, you're not going to come away with this lecture with the ability to implement finite element, boundary element, method of moments. But what I do want to do is give you a framework or a base to work from so that you can go off and read the books and literature and understand the methods much more easily. So that's the purpose of this lecture. We're going to start off by giving a quick overview of what variational methods are, what their benefits are, and then when we get into the meat, we have to discuss something called the Galerkin method. And this is the technique that we are going to use. It's not the only one, but it's the technique that we'll discuss where we'll take a differential equation and convert that to matrix form, much like what we did with finite differences, but this is just a different route of doing that. And I'll give some examples. Then I'll go into some detail about the finite element method and how that works, then method of moments, and I'll briefly at the very end touch on some other techniques that's in the literature that are also very powerful, a boundary element method and spectral domain method. So there are at least 4 broad categories of variational methods. Probably the most famous one is the finite element method, and we see this all over the place. You probably have seen the meshes where there's little triangles or tetrahedrons everywhere, and you break up a structure into little pieces of those triangles or tetrahedrons, and that's finite element method. Similarly, we can mesh the surface of an object instead of the volume. Finite element meshes the volume of an object, so you have elements through all 3 dimensions. Instead, suppose we could just mesh the surface. Well, for devices that are described very efficiently by their surfaces, these become very efficient. So the classic example is a sphere that has a minimal surface area to volume. So you would need many, many more volume elements than you would surface elements. So that sphere is probably much more efficiently analyzed with a boundary element method of moment type of technique than a finite element. Another difference I'll point out between finite element and boundary element, finite element is much more like the finite difference method. Your matrices look the same, they're sparse, you're coupling points to adjacent points, and we mesh throughout the volume, very much like the finite difference method. The only difference is the route we take from Maxwell's equations to the matrices. The other methods, the boundary element, method of moment, spectral domain, we're meshing the surfaces. And in this case, while we get away with many, many fewer elements, the matrices are full instead of sparse. So at some point, I don't know what the break even is, but at some point you get so many surface elements and the matrices are so full that you end up actually having a more computationally intense problem than going with something like finite element using many more points, but the matrices are sparse. So for example, imagine a very volumetrically complex photonic crystal kind of thing. That's probably more efficiently done with a finite element than a method of moments or boundary element, simply because there would be so many surface elements on that photonic crystal, probably just a slightly fewer more than there would be finite elements throughout the volume, yet with the boundary elements you have full matrices, finite elements you have sparse matrices. So for things described efficiently by their surfaces, the boundary element, method of moment type of techniques are king. Otherwise, the finite elements are. So when we're talking about a variational method, just like with finite differences, we start off with our governing equation, which was Maxwell's equations. We discretized them, we did some other stuff, and we ended up with Maxwell's equations in matrix form. We're going to do a similar thing here, except there's 2 routes we could take. We could take a true variational method approach and end up with a matrix equation from some differential equation, or we could go through what's called the weighted residual method. And for whatever reason, this seems to be the most popular. This is what we'll discuss in this lecture. But in either case, no matter what direction we take, we end up with Maxwell's equations or some differential equation in matrix form. The special case of the method of weighted residuals that we'll discuss is called the Galerkin method, and it'll be clear what that special case is as we go through this. So the method of weighted residuals is a technique for solving any kind of differential equation that is linear. So we can generally write it this way, where we have some linear operation. This could be the wave equation, operating on some unknown. This might be the electric field. And on the right-hand side, we have some kind of driving function or excitation. So that would be our source. So we can write the wave equation this way, the heat equation, equation of motion, a lot of differential equations we can write this way. Now, how do we know if this operation is linear? Well, it has to satisfy all of these different properties. If we perform this linear operation on the sum of two unknowns, that would be the same as the sum of performing a linear operation on the two unknowns individually. That's clearly a linear operation. If we multiply our unknown by a scalar, that can come to the outside of the linear operation. If we perform one linear operation on another, on an unknown, we can reverse the order of those linear operators. So as long as that linear operation satisfies these properties, it is linear, and we can proceed with our analysis. Next, we're going to define something called an inner product. This is just a way to compare two functions and see how similar or dissimilar they are. And so what we get from an inner product is a single scalar number, which is a measure of how similar those are. So we'll define it this way. If we compare two functions f and g, if f and g are so incredibly opposite and different that we'll call them orthogonal, that inner product will be 0. If we get a really, really big number, that means f and g are very similar. In fact, could be even the same thing. If it's a small number, well, they're not orthogonal, but they're very different. And what we tend to do is we scale this inner product such that if we compare a function to itself, which clearly should be the biggest number we can get, we'll just get 1. So our inner product really should be bounded between 0 and 1 by normalizing it. Some other properties that would define a proper inner product is this. If we compare f to g, that should give us the same number comparing g to f. That makes sense. It should be linear in some sense. And also, if these functions are different, we should get a number greater than 0. If we give our inner product a 0, we will get a 0 from it. Now, it turns out there's many different ways, probably an infinite number of ways we can define inner products. The most common and the one we will use to compare functions f and g is just to integrate over z. Now, if these are functions of two variables, then it'll be a double integral here, but we'll integrate over all the independent variables, in this case just z. We'll multiply the two functions together and integrate that over z. And so if these are orthogonal, overall f and g will be different enough that we get a 0 in the end. So that's the inner product that we will proceed with. It's just a comparison between two functions. 0 means they're very different, a 1 means it's the same function, and anywhere in between is just a measure of how similar they are. The next thing we'll do is expand our function into a set of basis functions. So in this case, f would be our unknown. That's maybe the electric field, which could look like anything. What we'll do is we'll expand it into a set of basis functions. You're already sort of familiar with this. When you took Fourier series of periodic functions, you expanded what was an arbitrary function into a set of sines and cosines. We did this with the plane wave expansion method, rigorous coupled wave analysis. We're expanding an arbitrary function into a set of basis functions. And we know everything about those basis functions. All we have to do then is weight them by some complex amplitude and then add them all up, and if we've chosen our basis functions correctly, we can get this original function. And if we put some smarts into how we select our basis functions, we can reconstruct our original unknown with very few basis functions. And that's the trick. How do we design the basis function so we can get away with as few as possible? So there's two different broad categories of these basis functions. We can choose basis functions that exist everywhere. So when we do Fourier series, we're decomposing a function into sines and cosines that exist everywhere over all time and space. Instead, we could also expand into basis functions that don't exist everywhere. They just exist at little tiny points. So for example, we have a pulse basis function, a rectangular basis function. It just exists over this interval. Outside of that interval, that particular one is 0 everywhere. The next basis function would be some number, or probably a 1 in this region, and then 0 outside. And so we can have triangular basis functions which overlap a little bit. These tend to be a little bit more efficient than the rectangular functions because it conforms more. These triangles conform more to arbitrary shapes, sinusoidal arcs, parabolic elements, all kinds of crazy things. But in general, we have the subdomain, which exists over one or a few elements, and the entire domain basis functions that exist everywhere. So what we want to do then, we have our general linear operation L operating on this unknown F with a source excitation G. Well, we'll take our F, we'll expand it into this set of basis functions and plug that expansion into our linear operation. Now we have this linear operation operating on a sum, which is what we have down here. Well, if this is a linear operation, we know a summation is a linear operation, we can reverse the order and we can bring that linear operation into the sum. Now we just have that linear operation operating on our basis function. This weight here is a constant. It can come to the outside and we end up here. And so we have our linear operation operating on our basis function. So another thing we consider when we choose our basis functions, what is an easy thing to calculate, so when we plug it into our linear operation, maybe that's the wave equation, that we can get an easy answer here. Now the method of weighted residuals. The next thing we want to do, we have this equation where we have a summation of some amplitude multiplying our linear operation operating on our basis function equaling an excitation. What we want to do now, we have this arbitrary function on both sides. We want to compare it with an inner product to some other set of basis functions that we'll call W. Could be, we could use the same thing as V's, we'll call that the Galerkin method, but in general this could be a completely different set of basis functions than what we chose to replace F. So then what we'll do is we'll compare both sides of our equation to W using the inner product. So we're taking W inner product with the left side, W inner product with the right side. And then we'll use properties of our our inner product to move things around on the left-hand side, and the right-hand side stays the same. So what we fundamentally see, we have the summation of a weight times an inner product. And what are we comparing in our inner product here? This new set of basis functions compared to our old set of basis functions with that linear operation performed on that. And on the right side, we're just comparing our new set of basis functions to our excitation. So this is the method of weighted residuals. It turns out this can be written in matrix form. This is completely numerical now. And we'll have a big matrix Z, which really comes from these inner products, operating on this column vector of unknowns, which are our weights now. And so once we know these, then we can multiply those by our basis functions, which we also know, and reconstruct our unknown. But we have this big matrix Z operating on our unknown coefficients, which were the weights on our original expansion functions, times a column vector, which is really a comparison of all of these different basis functions to the excitation. And so we can expand Z now, and what we see is each element in Z is a comparison of each different new basis function to the old basis function with the linear operation performed on it. So by first expanding F and then doing an inner product with this new set of basis functions, we've now made our governing equation, our linear operation, a matrix equation. Now the Galerkin method. What the Galerkin method is, it says this new set of basis functions that we'll use for our inner product, we'll use the same basis functions that we originally expanded F into. Because we probably put a lot of thought into this. It probably efficiently describes the field. It probably works very well with our linear operator. Why not just use those for W? So this special case, the method of weighted residuals, is called the Galerkin method. when our new basis functions and old basis functions are the same thing. So we'll take our original governing equation now and pull out the W and put in the same V, and we have a new matrix formulation. So very often just this alone is called the method of moments. Really fundamentally it's called the Galerkin method. And we can take any linear operation and put it in matrix form using it. So here's a quick summary of how you apply the Galerkin method. We start off with this linear operation. This is what we want to solve. This is what we want to put in matrix form so that we can solve it. Well, the first thing we do is expand the unknown functions into our basis functions. So we expand f, and when we plug this expanded f back into our linear operation, we end up here. We switch the order of the operations. We also bring this constant to the outside of the linear operation, and this is our final step after step 1. Then we take the inner product of both sides, comparing it again to our set of basis functions, and now this can be rearranged, and we have our final form, and this is what we use to convert to the matrix form. So the final step, step 3, is writing our original linear equation in matrix form. So this Z matrix is essentially comparing our basis functions with the linear operation performed on it to the basis functions in all different combinations. Our column vector of unknowns are the weights on our original expansion of f, so when we figure these out, we can just then multiply them by those basis functions and figure out what f was. And then our excitation on the right, this column vector is a comparison of our actual excitation to our basis functions. And we have a column vector of all those comparisons. So that's the Galerkin method on one slide. And we will use this to do finite elements, method of moments, boundary elements, and so on. Let's work through some examples. So here's a pretty good example. Let's say we have this differential equation that we want to solve. That's our governing equation. And so it also has these boundary conditions, and we're interested in finding the solution between 0 and 1. So this differential equation in this boundary with these boundary conditions. Well, and we want to apply the Galerkin method to do that. Well, one thing we can do is we can simply integrate this and find a quick analytical solution. So whatever our Galerkin method gives us, hopefully gives us that, because that's the answer that we can find real easily just analytically by integrating our differential equation. So let's see if the Galerkin method gives us that and under what conditions it does. And it will also illustrate how to use the Galerkin method. So let's choose this set of basis functions. So x minus x to the n. And I guess I'm skipping the reason for that selection, but we're doing two things. We want something that when we apply our linear operation to, it's easily evaluated, and that it represents the solution more accurately. And so we can kind of tell by the differential equation looking at it that we're not going to have sinusoidal or exponential type solutions. It'll look more polynomial-ish. So that's the reason behind this. So step number 1, expand f, that's our unknown, into that set of basis functions. So that's exactly what we're doing here. We expand f. Next, we want to choose our testing function. So this will be our new set of basis functions. So the Galerkin method, we use the same new set of basis functions as our old. So our testing functions, our w's, will be the same as the v's. We'll use the exact same thing. So when we take the inner product of both sides of our equation, we're going to use those same basis functions. So we know here's our original form, and we also know the final matrix form. We went through that. So in order to convert this to matrix form, there's two things we need to evaluate. We need to evaluate our inner products on the left, and we need to evaluate our inner product on the right. So there's two sort of analytical things that we have to do, but once we get equations for both of these, now we'll have equations to populate our matrices, and we can solve the problem. Okay, the first inner product. We are comparing, if you will, our basis functions to our basis functions with the linear operation applied to it, and all different combinations of those. So we have an m and an n here. So this is the definition of our inner product. We're integrating, in this case, over x. That's the domain that we're solving. And we multiply the two functions on either side in this inner product operator. So it's v times the linear operator on v sub n dx. Skipping a lot of algebra, and it's just calculus and algebra. Here's where we end up. So in this matrix ZMN, the ZMN element, which is the inner product between v sub m and the linear operation performed on v sub n, is simply this. And I think the trick is getting to this form, and after that it's just algebra and calculus. So we've done our first inner product. Now we need the second one. So here's our second inner product. We're comparing our v sub m to our excitation. So we write that inner product as the integral over x of v sub m times g dx. And again, now it just becomes algebra, and here's what we end up with in the end. Interestingly, it's a more complicated expression, but we've done it. So now we have to choose how many terms we want in our expansion. Well, let's just try one. So one term in our expansion. So we really don't even have matrices here. Just recall the derivations we did. This was the inner product on the left, the inner product on the right, what we got. And so now let's apply our equations to just one expansion function. So z11 in this case would just be 1/3. g1 would just be 11/30ths. And if now we solve our matrix equation for a sub 1, we end up getting 11/10. So finally the solution is we have our weight, we multiply it by the expansion function, and this is what we get. Well, this is not correct. That's not the solution that we already know that we found analytically real easily. So we need more than one basis function. Let's try two basis functions. Now we have a 2x2 matrix on the left. We're still applying these same equations to populate our matrices. So we go through the math. Now we need a z11, a z12, a z21, and a z22. And now we have numbers for all of those. Likewise, we need a g1 and a g2. So we plug all these numbers back into our original matrices and solve it for our unknown coefficients. And this is what we get. Now let's multiply these weights by the first two basis functions, and this is what we get. Well, that is still not correct, so we need a larger n. Let's try 3. And it turns out we still apply these same equations, we populate our matrix, and we get our unknown coefficients, and we have a 1/2, 0, 1/3. And then we multiply those weights by our basis functions, and here's our answer. And we did it. That is our answer. So we did this with 3 terms, and we converged to the exact solution. Well, what if we did 4? Skipping all the work, we end up with the same thing again. So in fact, no matter how many basis functions above 3, we get the same answer that we had with 3. So our method has converged. We've applied the Galerkin method to solve that differential equation. With that background, the Galerkin method, now we're ready to start looking at the finite element method and figure out how that works. And as I mentioned before, we're not going to be able to cover everything with the finite element. There's just not enough time left in this course. But what I think I can give you is a solid background or framework from which you can go read books and literature and I think understand it a lot better. So first is, what is a finite element? We know we're trying to solve for a function that exists over 3-dimensional space, and it is also possible to find an element in 2 dimensions and even 1 dimension. So we have this function that exists over 1, 2, or 3 dimensions. And what we'll do, just like we did for the finite difference method, we divide it up into a bunch of squares there. Here we're going to divide it up into a bunch of shapes, and I'm showing a triangle here on the left, but it could be other shapes. We have squares, we also have 3-dimensional shapes that we can pick. But the point is, we decompose whatever space it is we're talking about, and we we decompose it into these elements. And so all these elements should not overlap, and there shouldn't be any gaps between them. They conform perfectly. So think of putting together a jigsaw puzzle with these elements. Triangular elements I'm showing here for 2 dimensions, they're by far the most popular. They're pretty easy to analyze. They conform well to curved surfaces, whereas something that's square or rectangular, which is maybe a little bit easier math-wise, they don't conform to curved surfaces nearly as well. So you tend to see the triangular type elements in the finite element method. So this is, if you will, how we will discretize our function. And what we'll do is we'll do the Galerkin method on a single element. So we take our differential equation, we take how we define our element, we'll do our Galerkin method stuff. We'll end up with an equation associated with each element that then we assemble into this overall global matrix, which then we can solve and calculate our unknowns. So finite element always starts off with meshing. Before we even get to the math of solving the differential equation, we have to describe our geometry with a mesh. And this is a rather advanced thing. There's been many PhD dissertations awarded just on meshing algorithms. So I would put this actually at higher importance than the actual Galerkin finite element itself. And so we try to conform our mesh to curved surfaces. We can see these triangular meshes are doing that well. If there's regions, even if it's away from a boundary, but if there's regions where we know that the field is varying abruptly, we would probably put smaller triangles there. So suffice to say, there's a lot more to meshing that we're going to talk about here. We're just going to assume it can be done, and here it is. There is also something called adaptive meshing. And what you would normally do is you'd start off with a very coarse mesh, and you would do a simulation. And you would see certain regions where whatever function you're finding, maybe it's an electric field, in this case it looks more like a temperature profile or stress or strain. You look at where that unknown function is varying very abruptly, and you say, I probably didn't resolve that with enough elements. You'd go back into the mesh, you'd refine it in those areas, and then run the simulation all over again. And then you look at where the function is varying very abruptly, and you refine the mesh there, and you iterate that several times. And at some point, this all converges, where even where the field's varying abruptly, you have a sufficient mesh to resolve all that. And so doing this, that's called an adaptive mesh. Most of your commercial solvers have this built in, and it's happening in the background whether you see it or not. It's useful at this point to compare a finite element grid to a finite difference grid, and we can see some of the benefits of having finite elements. So let's say we have this arbitrary object with weird curved surfaces. Well, if we were to discretize this using finite differences on our ordinary Cartesian grid, well, we see that we can't get the shape quite right, and there's these regions where our model would think this is inside the material, but it's not really. And we've talked about some techniques for handling this, dielectric averaging and stuff like that, but the point is there's still some discretization error here. However, if we resolve this object with triangular elements, we can see that that discretization error, like right here, is a lot smaller than on a Cartesian grid. So while the finite difference stuff is much easier to implement, we lose some accuracy and even some efficiency. We lose the ability to do unstructured grids and other crazy things. I still love the finite difference method. For small things, it works wonderfully. Even for very volumetrically complex things, I think it's on the order of the same speed and efficiency as the finite elements. But for simpler objects like this, finite element is definitely king. But there still is a benefit to finite differences. If we wake up in the morning with a new way of how to whip around some differential equation and solve it, we can probably get that done in a few hours using finite differences. With finite elements, without a lot of experience with that, you're talking perhaps days to get that same implementation done. And even if you're good, certainly finite difference is a lot easier, and you can get to a solution, an analytical solution, or a formulation of your code a lot quicker than you can finite element. In finite elements, there's really two different categories of elements. There's what's called node elements, and there's what's called edge elements. So node elements were the first invented, and we have our ordinary triangle, but we say that we're only going to know and store the field value at the vertices or the nodes of this element. Anywhere else inside or outside the element, we're doing some kind of interpolation to figure that out. So this is very much like the finite difference method. We only know the field at discrete points. However, this does not inherently satisfy the divergence condition, so we have this spurious solution problem with node elements. A benefit of node elements is that the matrices that we build, they're pretty well conditioned. So if we have an iterative solver, they tend to converge faster than the edge elements, which I'll describe next, which have a poorer conditioning. So for the edge elements now, instead of knowing the field at the vertices, we know the fields at the boundaries. And notice those are the tangential components. So since we know the fields at the boundaries, if we look at an adjacent element over here, it shares this field value. So we really are enforcing the boundary conditions between the elements. So we don't have the spurious solution problem with the edge elements. However, the matrices are conditioned more poorly. So I'm starting to see more papers now actually go back to the nodal elements as people are trying to implement finite element on GPUs and other types of high performance computers. So it's an interesting trend. We almost abandoned the node elements for these edge elements, and now with GPUs and stuff like that, I'm seeing more and more papers now going back to the node elements. So from our discussion so far, we know that we're going to expand our unknown into a set of basis functions. In this case, those basis functions we will call shape functions. So within an element, we want to know maybe the electric field. And since we're using triangular elements here and node elements, we're going to know the field at 3 points. And so it turns out we will have 3 shape functions within each element. So if we have 100 elements, that's a total of 300 shape functions. But within one element, we only have 3. And so if we know the value at node 1, this would be the shape function associated with the value at node 1. If we know the value of the field at node 2, here's the shape function for it. If we know the value at node 3, here's the shape function for it. So really, if we know the field value at all 3 points, it's a linear sum of these. And so that's exactly what's happening. We sum our 3 shape functions, and u sub I really is the electric field value at node I. So what do our shape functions look like? Well, they're planes, right? So here's the equation for a plane. Then here's where I'm skipping a lot of stuff, but we'll have what's called the element matrix. So we start off with our governing equation, and in this case it's our wave equation, and we go either through the variational method or, like we showed, the Galerkin method, and we end up with this in matrix form. But we will apply this only to one element, and one element only has 3 unknowns. So we have this column vector of our 3 unknowns, and there may be some kind of source or excitation associated here, or maybe not, but there's potentially 3 numbers over here for a source or excitation, and then all the other math stuff gets lumped into this matrix that we were calling Z. Now we're calling it K. So the superscript E is saying this is for element E. So here's element E, and here's a 3x3 matrix associated with it. So you can imagine now meshing an object, and then for each element, you calculate its element matrix. And so that's what we're showing here. And somehow, we want to lump all these element matrices together into one big global matrix. And that's what we're talking about next. So that's exactly what happens. We have one big global K matrix. So we were calling this Z before. We have a whole column vector of the fields at the vertices. So those are our electric fields. We have K, which is assembled from all of the element matrices we talked about on the previous slide. And then B, which is our excitation vector, which is also assembled from the element matrix equation from the last slide. So we set up a loop, we go through all of our elements, we calculate the element matrix, put it in the global matrix, and when we're done looping through our mesh, we have our global matrix, which then we can solve. So let's talk about assembling the global matrix. So let's say we have this problem. we have a Pac-Man looking thing. So it's almost a circle, except it's missing this lower left quadrant. And here we're using not a triangular element, but a quadrilateral, I guess it's called, but it has 4 vertices. It's not a square. And so we have 3 elements now describing this Pac-Man shaped device. And so globally anyway, we can forget about the element for a second and label all of the vertices as unknowns. So these circled numbers are the global node numbers. So we have a 1, a 2, a 3, a 4, a 5, a 6, a 7, and an 8. And so that describes our overall number. One thing we'll need to do when we calculate our element matrix for these different elements is map the local node numbers to the global node numbers. And that's our guide that we use to assemble this global matrix from the element matrices. Now, in this case, we have 8 unknowns. So our K matrix will be an 8 by 8 global matrix. Our elements in this case have 4 unknowns. So they themselves will be 4 by 4 matrices. So somehow all of these different 4 by 4 element matrices will get lumped into this big K, this big global 8 by 8 global matrix. So we'll have 3 of these because we have 3 elements. And we start off, we initialize our global matrix all to zeros. Step 1, initialize the global matrix all to zeros. Now we look at element 1, and we assign local node numbers. So again, we'll do it counterclockwise. We'll call this one 1, 2, 3, and 4. So in this case, we can make a little map. Local node number 1 corresponds to global node number 1 also. So coincidence that they're the same. Local node number 2 corresponds to global node number 8. And we can see that over here. Local node number 2 corresponds to global node number 8. So we finish this, and then local node number 3 is global node 3. Local node 4 is global node 2. And so using this, we can map elements from our element matrix to our global matrix. And let's see how that's done on the next slide. So what we're going to do, we're going to take the element matrix for this element, which is a 4 by 4 matrix, and populate the global matrix with it. So remember, local node numbers to global node numbers. We're going to use that. So where does local K11 go? Well, 1, 1, it's going to go to, so K11, it has 2 subscripts being the local node number. It'll go in the 1, 1 position in the global matrix, which is exactly where it is here. It's in the global 1, 1. Let's think about local 1, 4. Local 1, 4 will go to global position 1, 2, which is exactly where it is. It's in the 1, 2 position, but it's local 1, 4. What about the 1, 3? Local 1 and 3 goes to global 1 and 3, and that's exactly where it resides. Let's look at this one. Local 1, 2, where does that go? Well, local 1 and 2 goes to global 1 and 8, and that's the position, global 1, 8. So we have a 4 by 4 element matrix, and we go through all 16 elements of that. We figure out where it is locally, map it to where it needs to go globally, and we add it into the global matrix. So we've populated now the global matrix with the first element. We do the exact same thing for the second element. We go element by element, we map local to global. Let's do a few of those. Let's think about local for the second element, 4, 4. So in this case, we're talking about this node. So local node 4, 4 is global node 3, 3, which is exactly where we put this. Now the trick is when there's already an element built into the global matrix where we add the elements of the second element, we add the elements of the third element, and so on. So we don't overwrite, we add to. So if we work through this, that's exactly what's happening. We've added all the elements from element 2 to the global matrix. So where there was overlap between where we've placed elements from element 1 and elements from element 2 is here. So this is one where they both added. Here's another area where they both added. And here's another area where they both added. Then we go on. Now we're at the third and final element. We do the exact same thing we did with element 2. We map the local to the global node numbers. We calculate the element matrix, and we populate the global matrix for that. And if there's any positions where there's already numbers, we add 2. So we can actually see there's one position in this matrix where numbers from all 3 element matrices added together. Well, let's do a quick example here. Let's look at local K13. So local K13 goes to global 7, 5. And that's exactly where this is. It's the 7th row down and the 5th column over. And if there was already a number there, we would have added to it. Not overwrite, we add to. So that's the procedure going from our element matrix to the global matrix. We do the exact same thing for that column vector B. And we see there are some places here where we're also adding 2. We never overwrite, we add 2. Now we're ready to solve the problem. We have our big global matrix K. We have our source column vector B. And we can bring K over to the other side and backward divide and calculate the electric field, in this case, at all of these unknown nodes. And that's it. That is the finite element method. There's another thing that's becoming very popular in finite elements, and it's domain decomposition. And what this allows us to do is we not only mesh an object, but we'll take one portion of that object, maybe send it to one CPU, take another, send it to another CPU, and they can do their number crunching and iterating back and forth in parallel. And so this really speeds things up. Rather than having one CPU looking at the entire problem, we have one CPU working at a little smaller part of the problem, a second CPU looking at another problem, another part of the problem, and so on. So that's called domain decomposition. It actually speeds things up quite a bit. But it requires systems that have multiple cores and fast communication between the cores and memory. So that concludes our discussion of finite element. A very related method is called method of moments. Let's talk a little bit about that. Some very common places that we'll see method of moments is for thin wire structures and metallic sheets. And the real neat thing about method of moments, there's no boundary conditions. Like in finite differences, at the edge of the grid we had equations that needed values from outside, and that was a problem we had to resolve. Finite element has the same issue. We need boundary conditions here. With method of moments, there are no boundaries. We do not need boundary conditions. That's very cool. And the math really simplifies down, particularly when we're modeling metallic structures. So if I see an all-metal structure, thin wire antenna, or something made out of metal sheets, I'm immediately thinking in my head, this is going to be great for method of moments. For thin wire devices, there's a bunch of different formulations. The 3 big ones are Pocklington's integral equation, Hallen's integral equation, and then another thing called the electric field integral equation, which I'm not showing here, but it's similar to these. Pocklington's integral equation and Hallen's integral equation, you'll notice are very similar. One difference is this linear operator sits inside the integral in Pocklington's integral equation, and Hallen's, it comes to the outside. And it turns out this numerically is a little bit better, although this is more difficult to implement, but numerically it's a little bit better because we're dividing by r here. And this r term can go to 0, which of course makes this go to infinity, and that's called a singularity. And so we sort of have this sharp spike here. And to make things a little bit worse, we're taking a second order derivative of that sharp spike. That's bad. So if we move that to the outside of the integral equation, which we're free to do, we're just swapping the order of linear operations, now we have this integral happening on this sharp pulse-like function, which tends to smooth it out. So numerically this behaves a little bit better, although it's a little bit more complicated to implement. But Pocklington's integral equation is sort of method of moments 101 for thin wire antennas, although Hallen's integral equation is a bit better behaved. We can also apply method of moments to structures, and here we're meshing the surface now, not a volume, And the most famous element here, it's an edge element called the Rao-Wilton-Glisson, or just an RWG edge element. And that's probably the most famous element there is. And so metallic structures, we can just mesh the surface. This is the way to go. This is very, very fast and efficient. Within the method of moments, there's something called the fast multipole method. Remember, these method of moments, these integral type equations that we're solving, they have full matrices, and that can be a problem. What the fast multipole method does, now let's say we're writing an equation associated with one point here. We have all of these points far away that would ordinarily require a lot of stuff. Instead, we can treat these all as one single point, as long as it's very far from where we're writing our integral equation for. So in doing this, that is the fast multipole method, and it lets us get away with much smaller matrices. They are still full, but they're much smaller. And people have really accelerated the speed of computation using this. And the last thing I want to mention is just some other worthy methods. We have the boundary element method. Very often this is just called the method of moments because before we were meshing the surfaces of metallic objects, but we can also mesh the surface of dielectric objects. So there's the boundary element method, and this is very good for when we have structures described very efficiently by their surfaces. If we have a lot of surfaces, a lot of volumetric complexity, this probably is not the best method. Like the method of moments, there's no boundaries here, so we don't have to worry about boundary conditions. That's very useful. Another thing you see, speaking of the non-boundary condition thing, you'll see hybrids of finite elements and method of moments, or boundaryless methods. So you'll resolve your device with a finite element mesh throughout its volume, but then on the very outside, you match to like a boundary element or method of moments, which then does not require boundary conditions outside of that. And then the last thing, spectral domain method. Think of this as the method of moments or boundary elements, but in Fourier space. So it's very good for periodic structures, although you'll see it in some old papers doing transmission line analysis and other stuff with it. So that concludes the variational methods.